So it's an honor to be here at Georgia Tech. Thanks, Doug, for referencing my time here. When I went to Georgia Tech, this didn't exist. So it's good to see that the college continues to develop and advance. What I'm going to be talking to you today about is a new paradigm for manufacturing. And my co-presenters set me up really nicely today. So thanks to Marty for that wonderful intro. You used all of the words that I'm going to share today, so I don't have to define anything. And thanks. And so what we're going to be talking about is basically a new paradigm for manufacturing food. It's the idea that contactless manufacturing has arrived. Now, to my JBS colleague that shared some really challenging use cases, it does not go all the way into meat rendering, but it's going to apply broadly to most of the food industry. And so that's one of the things that I want to leave you with today, is that if you're not incorporating these type of aspects into major renovations or new plant design, then it's time to kind of take a pause and reevaluate where you're at. Hopefully some of the things I share with you today are new to you, and you say, wow, I didn't really realize that was happening. There we go. Okay, so what are we going to go through today? We're going to jump in. We're going to share some details about the paradigm, just like the high-level thought piece. Then I'm going to benchmark on what's happening in autonomous vehicles. So as a spoiler alert, we're going to be talking about autonomous vehicles in factories. We're going to be talking about cobotics, which we already had a couple lessons on. We're going to share some details on use cases. So these are facilities that are recently stood up with at-scale implementations. We're going to share a design guide so that you've got, that's when you get your camera phone out, you take a picture, and you'll have the cheat sheet of how to do it. And then finally, we'll bring it home with the economics and share what some of the cost drivers are that make this compelling. So first off, I'm going to argue that proximity no longer matters. And that's incredibly important because we talked a lot about legacy factory design already today, and everything fights for the same proximity. Sometimes when new processes want to be added, buildings have to be modified. So what we're going to argue today is that proximity no longer matters. The aspect of manufacturing line and closely coupled elements is going to start to deteriorate in the coming ages of new technology and implementation. Also, we also talked about material transport and repetitive jobs, ergonomics, and those sort of things. So when product transport is solved, people can start to innovate and either focus on new ways to improve or continuous improvement. Department of Labor estimates that in some factories, up to 70% of human effort is on material handling. And so what we want to do is take a big swing at that and drive that down. What are the unlocks that we're going to use in this new paradigm? Autonomous robots, collaborative robots, i.e. cobots, real-time inventory software that's going to help us with our traceability, fleet management, and then inventive tooling. One of our speakers already talked about, don't worry about robots taking over. We can barely get them to do what they're designed to do. Another thing I like to point out is robots really don't have hands. So they're not taking over much of anything yet. So that means we have a lot of gap to make up in terms of tooling and manipulation. So this is the basic theory, which is everybody in here that has factories or goes to factories or has a lab has islands of automation. You have little islands inside of your plants that are incredibly intelligent, loaded with sensors, PLCs, advanced software, sensing, and there's a lot happening in there already. However, across the different islands, they're like an archipelago. They could all speak different languages. So what we now want to do, and this is making best use of legacy technology, of making best use of what we already have, is we want to link those islands together to form a network. What that network does is it creates a network effect. You hear that word talked about in social media or anything that's subscriber-based with more and more subscriptions. But we also want to apply that to machinery. What is our machinery capable of when we add more machines to a network that's all collaborating? Okay, so to do that, I'm going to benchmark you on current state technology. So everything I'm going to show you here is more recent than 12 months, so it's what I consider very current. So what is happening in autonomous vehicles? Well, on the bottom right-hand side, you see Waymo. That's the company founded by Google. They have an approved for public use robo-taxi, level 5 autonomy, that can drive with no human driver inside the vehicle and is cleared to move passengers. There's currently 2 companies that have that same certification from NHTSA and the US DOT. So there's at least 2 companies that are moving passengers with no driver right now, just the AI brain of the vehicle. On the upper right-hand side, you see what is basically a level 4 autonomous public transit vehicle. The US DOT is sponsoring 3 pilots right now, one in Jacksonville, one in Youngstown, Ohio, and one in Las Vegas, where they're sponsoring these autonomous mass transit shuttles. That is the here and now. There are probably dozens of pilots deployed around the country, and Atlanta has actually sponsored one in the past. And then on the right-hand side, you see these kind of sidewalk vehicles that are getting a lot of investment, a lot of hype in Silicon Valley, and that's around owning the curb space. How do we get goods to the doors? You can see the form factor of that vehicle doesn't even anticipate a human. It's only looking for goods to be delivered to a doorside. And that, I think, is a more realistic vision of Amazon's drone concept, is let's actually drive the goods to somebody's doorstep. Okay, so that's on-road. On-road has the most challenging ODD. When we're talking about autonomous vehicles, we're very focused on ODD, which stands for Operational Design Domain. And there's a lot of rules. We got kids on skateboards, we got handicapped people, we have mixed traffic, we have the unpredictability of weather. So if we strip some of those constraints away, we have a really exciting part of the industry, which is off-road autonomy. Off-road autonomy is moving really fast, and you've no doubt heard about use cases in things like mining and other kind of hazardous 24/7 type operations. So I've got some very recent examples to share with you. Number one, on the right-hand side, let's get out of the way. You can't talk about autonomous anything without having Spot the robot dog. I'm sure he's been here on campus more than once. What I like about Spot is Spot sees staircases the same as he sees a sidewalk. He'll walk through a doorway and enter a new design domain without the concern about navigating. So the navigation package on this robot is very advanced. On the top left, you'll see a new autonomous tractor that's been launched. The form factor of this one is specifically catering to the grape industry in California, but it could be anywhere. And what it's doing is it's unlocking a labor component. So the vehicle can drive and, for example, spray grape leaves with some sort of insect repellent once a week or every other week with no human driver. It also comes with a toolkit where the farmer can use it as a power supply to do things like welding out in the field. So this has become basically a toolkit and an autonomous labor remover for major industries. And once they get it working in grapes, which is a high value crop, you can see it coming down into other agricultural spaces, maybe with lower commodity values. And then on the bottom left-hand side, you see an 8-wheeled vehicle that can navigate through the brush, through muck and mud. And so this vehicle needs no fixed monuments to know where it's going. It's operating almost entirely off of GPS and a sensor fusion of what it can see. Is it going to be accurate enough for what we need it for? Maybe not, but it just shows how diverse the use cases are in vehicles that are actually running right now. Okay, next we're going to jump into some use cases. So I'm going to show you some descriptive statistics on some actual factories that are running autonomous technology on a 24/7 basis. So that we cover the gambit, on the right-hand side we have greenfield facility, left-hand brownfield. So I'll just give you some high-level stats. The greenfield facility is a 1 million square foot facility. You know, those are nice and big. Those are hard to get around. 400,000 square feet of the facility is zoned for AMRs. AMR stands for Autonomous Mobile Robot. It's a unit load system, so it's replacing anything a human would have done. So in a lot of factories, humans push carts. The carts could be loaded with tooling, could be loaded with raw materials or work in progress. In this case, the autonomous robot can carry a human load. So it's going to replace that size. And then one of the interesting things is, because it's a from-scratch design, you get to take the best from different industries. So in this design, there's an e-commerce pick interface inside of a factory, which means you get all the efficiency of e-commerce zone pick. It's not something you hear about in food factories often. And then you have machine-to-machine exchange of materials on the other end. Because we're buying new machinery, we get to decide how the machines receive their raw materials. In this case, let's go ahead and have an automated exchange between robots. So those are two very different use cases that are happening on the same end of a single mission. The next is how they communicate. It says connects islands of automation. We have to have multiple communication formats. We want to make best use of IoT, but we're also going to use things provided by the client's host network. And then on the bottom you see statistics of just kind of how robust the system is. This is literally working like a Delta frequent flyer. So there's 1,100 miles per day traveled. If that was not with robots, it would be traveled by humans. So that's 1,100 walking miles per day that have been replaced. And then 5,200 missions. And so think of what that adds to the robustness of your traceability and your transparency when you have real-time track and trace over that many transactions that previously would have been generally unrecorded in a factory. On the left-hand side, we're talking about pallets. So brownfield facility, we had a different use case. We had to figure out how are we going to move pallets around a facility that is a flagship facility for a major consumer goods manufacturer. It's completely congested. There are way too many manufacturing cells in the plant. There is not enough space for inventory, so how on earth can you implement new technology? So in this case, it's pallet handling, and the short answer was, let's make best use of what we've got. There was an existing V&A storage system. Let's get the vehicles communicating with and taking goods out of an existing manual V&A. There was legacy assets that just could not be taken down for a minute, such as centralized stretch wrap stations. Let's go ahead and modify those so they can work with autonomous robots. And then there was existing legacy packaging lines and all sort of equipment that we've talked about already today, and it all has to go to a warehouse. It all has to get automatically staged up for truck loading. So how can we make all that work? Well, we've got local AI on board the vehicle. That is the unlock that allows the vehicles to nimbly go down the same paths that manual forklifts and humans currently use. Multiple sensors to assess the environment. There's two reasons. One is we need to be highly accurate in how we interact with product. The other is we need to be extra safe in how we work around people. I know Wi-Fi and IoT communications, again, we're in generation 1 of this type of design theory. We're already using multiple communication formats. And then we need maps that discern permanent from temporary. If you have the benefit, if you only have laser vision, which is how these vehicles see, then it's going to be very confusing that from what you can see, the factory changes all the time. How do I, as the robot, know that the box that's placed here is temporary, or the legs I see standing there are temporary? Those are human legs. The legs on that machine are permanent. So we had to come up with kind of some rules on teaching the robots how many things can move and you can still orient yourself based on what you can see. Another great use we have is slow zones and high speed zones, where we take an architectural layout and we overlay pedestrian paths. We go ahead and program in a low speed zone. Let's go ahead and slow it down because we have a high frequency crossing. And then for high speed zones, hey, the name of the game is efficiency. We want to travel as far as we can, as fast as we can. So anytime we have a corridor where we can let the vehicle go to its max speed, we go ahead and open it up. And then finally, opportunity charging. The vehicles work off lithium ion. The rule of thumb is for unpowered tooling implements and for relatively low payloads, the vehicle can work for 8 hours and charge for 1. If you go to a heavy payload or a powered tooling implement, then we're going to drop that ratio down to about 5 to 1. So we need to have opportunity chargers spaced throughout the facility. And then I'll show you what it looks like, so we're not just talking pure theoretical. So here you can see we're testing how to get an autonomous robot to interact with a machine. This is just a test that we did before we deployed anything. A light turns green, there's a Bluetooth handshake, and then we exchange a unit load. Of course, you scale this up to a factory that's 1 million square feet, and it looks a little different than that, but this is the basic theory at work. In the back, you can see a bunch of tooling implements that were created specifically for materials. Here you're going to see lights out, picking up the infrared of the LiDAR overspray. So that just shows what the vehicle's using to scan the environment. Here you can see a factory worker that is being literally taught maintenance on an autonomous vehicle. So that's exactly the workforce principle we've been discussing. This is a view of the fleet management software that's coordinating different vehicles, and on the left-hand side are all the missions being monitored for execution. This is the idea of mixed fleet. Everybody's seen an AGV before. We're doing a high precision pick with forks. In that case, we need to have different vehicles with different form factors, and we're not afraid to mix types of vehicles in our fleet. This is a performance test where we take our autonomous robots, we lay down some wooden pallets in their travel corridor and see if it causes any missions to jam or fail to perform. Because of the technology and because of the layout, the mission success rate remains at 100%, even with those physical obstacles put into place, and we don't confuse our navigation. This was a performance test. We put a lot of robots in a very complicated room that had to perform a lot of missions. And my head engineer goes to the power panel, pulls the disconnect. On the vendor side, everybody gasped. The robots didn't even notice. They're using LiDAR, so they don't care whether the lights are on or off. That's just for human convenience. Here's an example of ergonomic improvement. So we have a tooling implement for the autonomous robot that can carry a very heavy reel. How are we going to get that reel into position over and over and over again without creating an ergonomic challenge? Here's the types of simulations that we perform. And what you do is you basically take a full year's production schedule, run it overnight on a supercomputer, come back the next morning, and just like the lady showed us on their spatiotemporal analysis, where do we have hotspots, where do we traffic jam, where do we fail? So here we've just turned on the remapping function. You can see the green dots are LiDAR overspray. They're constantly seeing the facility and they're creating a reassessment of what do I expect the facility to look like. So we're remapping on the fly. This is going to show you basically the precision of the vehicle. It's free navigating. There's none of the fixed monument stuff you're used to seeing with other types of vehicle technology. It's going to be a pretty precise pick and location. You can also see these videos are time synced on the right-hand side. The fleet management software is perfectly in real time with tracking the movements of the vehicle and the deposit of the payload. All right, and the completion of that video makes me very happy because that means our commissioning team was successful. And I'm not sure we had 100% confidence in that when we designed the system, but when we got to the end, we felt really good. So, all right, next we're going to look at our design guide. So now I want a contactless system. I want robotics that operate around people safely. I want a 24/7 operation system. That's powered by artificial intelligence. It's got the same technology as a Google vehicle. That's what I want. How do I do it? So this is kind of your design guide. Number one on the upper left-hand side is the drone head. The drone head is kind of the industry buzzword for the AI package mixed with the sensors. So it's comprised of vision system, sensor fusion, the firmware, which is what I call the AI, and then also the industrial compute. These vehicles that you saw in those videos have enough onboard computing power to be a Bitcoin node. I mean, so these things are pretty powerful. That alone consumes most of the power from the vehicle. On the bottom right-hand side, it all has to go somewhere, which is fleet management. We might be managing a mixed fleet. We certainly want to begin to create real-time inventory insights, and then we want to deliver some sort of analytics to the enterprise. And that's kind of an argument that we make, is that with any major digital project, companies should expect to have new enterprise level insights. I won't go into extreme detail on the others. Communications, you can see we're using multiple communication formats, including low power consumption like LoRaWAN. That's very important, especially as we want to deploy remote sensors. For tooling and manipulators, we kind of start by bifurcating. Is it a powered tool that's going to take power out of the lithium ion kit on the vehicle, or is it a non-powered tool? And then that gives us a lot of options. The bottom line there, though, is ergonomics. We measure, and you have to improve the ergonomic load on the employee. And then in the middle, you know, it's important to understand your cost drivers, especially as we talk about inflation, supply chain, and those sort of things. Roughly 50% of the cost of an autonomous robot system is comprised of the chassis, steel, the battery, lithium ion or equivalent chemistry, the motors, and the charging. So right there, and basically the physical thing that you see is half the cost. Okay, and the next thing we'll do is we'll take a peek at the economics. and just see kind of why this is compelling and why we're arguing that it's not just a fancy toy for some corporations. This is the new paradigm. So we have done the analysis, and for autonomous robots replacing human load scale, it's a little small, I'll read it to you. At the top left, it's 1/10 the cost. So if you're paying people to move stuff, if you can convert that function to be an autonomous robot function, it's 1/10 of the cost. Of course, the robot works all shifts, and the robot also gets less expensive over time as the asset depreciates and pay wages go up. You're fixed into the robotic cost. If you're manually moving pallets, if you're using a forklift, then the cost is 1/5 of the cost to go to autonomous robots. So anytime you have a large contingent of forklifts and you want to start to remove some of that fleet of forklifts, then you're going to face a 20% of the cost, or a 80% cost reduction to go to autonomous robots. The comparison isn't always black and white. In a new facility, we might be comparing against mechanical automation, so we've done the conveyance and the AGV. Autonomous robots are half the cost of conveyor. We greatly prefer autonomous robots to conveyor because they're flexible, we don't have to rip anything out, and it changes with us in the future with a simple remapping. That process can be done by an in-plant technician, does not require calling a millwright or an integrator. And then on the bottom, you see basically autonomous robots versus automated guided vehicles. Autonomous robots are about 2/3 the cost of automated guided vehicles. They're a bit cheaper. However, there's a few less things they can do. We noted the fork activity earlier. And then coming over to the left-hand side is, what about our people? That's the ergonomic component. So what is the cost of not having stress and strain related injuries? That's a huge thing. What is the cost of creating basically a career path for employees to where they don't see themselves as manual labor job performers on an hourly basis, and they're considering going to the Amazon facility down the street, but they view our company as a career path. So that's another huge thing. The ergonomics, we use the NIOSH standard to analyze people's workloads, and we always go for two intensity grade reductions to every employee before we consider that the job is done successfully. And we do that with things like the tooling and the lift assist that you saw earlier. All right. So with that, I think that's the end of our contactless journey, and I will open it up for any questions that anybody has.
Yeah, I think this is not a brownfield facility where you have a fleet of autonomous vehicles. What failure recovery procedures do you have there, and do they require a specialist from your firm, or can they be done on field personnel?
The intent is to always do it within the field. So there's a transition of care period where you still want the original technicians and engineers available, but the intent is always to get it to empower the local plant staff. So for failure recovery, there's kind of a couple different modes of failure. One is just a robot hardware failure. So does anybody in here have a Roomba? Right, like what's the failure rate on the Roomba? It's like 50%, right? Or, it depends on if you have kids. Then it's a 90%. So it's very similar here. Is that occasionally you're just going to have unexplainable hardware failures where the vehicle gets confused, or it allows its battery to get beyond a critical level of management, and it just needs manual recovery. Somebody has to go plug into it and drive it out with a little PlayStation controller. So that happens. That becomes rare. The better systems get managed, that decreases in occurrence dramatically. That's something that we've learned. We didn't know that till recently. Another type of failure is new business rules. That's the one that is probably implemented by plant teams. We allow that software interface you saw for fleet management, we allow the plant teams to have user access to that and admin access. And so a plant team may have the best intentions in heart, but didn't have the benefit of being engineers and studying all the potential failure modes ahead of time, so they may have put in conflicting business rules. And unfortunately, the AI is still at the first generation, so it doesn't necessarily catch that that's an error. So you can confuse it, and we've done that a couple times. A vehicle might try to pick up a payload when it has a payload, for example, and then it encounters an error when it tries to perform that function. But generally speaking, once the systems are commissioned, they tend to get a little bit better, because you can configure the maps for performance zones, and what the plant people do is they change the maps. You can install a roundabout, for example, to have better traffic flow. You can install a four-way stop. You can do the slow zone or the fast zone. And so usually it's a behavior thing, and then the other thing that happens is local plant employees start rallying around an automation culture, and as that happens, people stop doing things like leaving broomsticks where my robot has to dock. That will cause a failure. So hopefully that explains it.
So just to follow up on that,
Yeah.
Do the systems have like online learning? So if there is an obstacle in the path of the robot, does it learn to like plan around it for a particular?
Yeah. The whole AI pieces, these are not fixed route like most people in here have seen AGVs before that are on a rope. Basically, they're on a train track, virtual train track. These absolutely re-navigate. They'll change aisleways, they'll change approaches, they'll wiggle around something if they can do it and keep within their safety parameters. And then, like I said, the map is updating. I showed some maps that were being updated in real time. If it sees it enough, it will assume that's now part of the facility, and it will relearn it collectively as an entire fleet. Yeah, go ahead.
To that end, is the path planning handled by a centralized server, or does each individual robot control its own path planning?
Each robot controls its path. It gets a mission dispatch and a priority from the central system, then each robot controls its own path. Yep. In the back.
So space restrictions in our poultry industry, space is very limited, and of course there's overpasses. You have to go up the steps and all that, and that's why I don't have a Roomba, because I'll have to buy 3 Roombas. But I have seen it though. I have challenged a robot in Lubbock Airport, standing in front of it. It will wipe the floor, and I'll stand in front of it, and it stops every time. And I have tried to cheat it, it still stops. So I do believe it works, but with the space restrictions though, and spatial considerations, I mean, is that something that's going to be a challenge?
Yeah.
Is it?
That's a good question. So we don't have a way of thinking yet that solves multiple level manufacturing. So in the multi-level situation, you still need multiple Roombas, or you need to physically carry them between levels yourself. You need to choose that. But in terms of space restriction, the reason that we took on these ambitious projects that were pretty high stakes, certainly for us reputationally, but also for our clients operationally, was because we first tried a full conveyance design, and it looked terrible. So I think our gentleman from the automotive industry would have something to say if he'd seen how much conveyance it would have required to move these materials automatically. Second thing we tried was AGVs. Why? Because it's proven technology, it's been around forever, established vendor base, safety protocols, etc. However, AGVs cannot get through tight spaces, and they can't figure out traffic jams. They need to have dedicated aisleways, pretty much that are human-free and mixed traffic-free. So that led us to start exploring this technology, and what we found was we could safely get through really tight corridors in existing brownfield plants that were very stuffed. So this, from a space perspective, you don't give up a lot. You'll have to find some parking spaces here and there, which you have probably in pockets, and you'll have to find some charging zones, which you could probably make space for if you clean up a little bit. So that's it. Yeah.
Good, thank you, Matt. Appreciate the presentation.